All right. Let's continue our discussion on graphs. We briefly introduced graphs last lecture and discussed undirected graphs versus directed graphs, some differences, and we saw this very simple basic search algorithm. In undirected graphs, if you start at a vertex, you can find all the vertices that vertex can reach by doing a simple basic search efficiently, right, in linear time, right? So that will find in undirected graphs, the structure is that you have a bunch of connected components, right? And if you start searching from a vertex, you will find all the vertices that it will reach, which is the connected component containing that vertex. And then once you find that, you can check another vertex which is not already been found and find the connected component that it reaches and so on, right? So you can do all this in linear time to find the structure, basic structure of an undirected graph, right? If I have a directed graph, things are a bit more complicated because of the reachability relation is not symmetric, right? So if you look at this graph, the vertex B can reach the vertex G, right, by this path, but G cannot reach B because G has no edges out, right? So the reachability relationship is not symmetric, so we need to think a little bit more carefully about what the structure of directed graphs are. So there is a useful notion of connectivity in directed graphs, which is namely the strong connectivity, right? We say that two vertices U and V are strongly connected to each other if U can reach V and V can reach U, okay? So in this example, B and E are strongly connected to each other because B can reach E, right? And E can reach B, right? Yeah? Agreed? So, yeah, any question? Sorry, was it a question or a discussion? So on the other hand, A, for example, can reach B, but B cannot reach A, right? So they're not strongly connected to each other. Okay. So we can reach that, we can say, what does this relation do? I mean, if it has certain properties, right? Clearly U is strongly connected to itself, right? And by definition, if U is strongly connected to V, V is strongly connected to U, right? Because the way I defined it, it's symmetric, right? And it's also transitive. What does that mean, transitive? That means that if U is strongly connected to V and V is strongly connected to W, then U is strongly connected to W. Yeah? Why? Because, of the way we define it. If U can reach V and V can reach W, then U can reach W. If V can reach U and W can reach V, then W can reach U, right? So so because this is an equivalence relation, it is symmetric, reflexive, symmetric, and transitive, it induces an equivalence relation. And what does it mean? If you strip away the math, you get what are called strongly connected components. That means that you can partition the vertices of the graph into sets, right, such that each of those sets is a strongly connected component, and two vertices are strongly connected if and only if they stay in the same component. Yeah? Okay? So what are the strongly connected components in this graph? Yeah? Okay, I claim that, sorry, B and F. But see, we want maximal strongly connected components, not just, what does it mean to be an equivalence relation? That is the maximal set such that they have the relationship. So we need to include everything that is in that component. So if in this graph, this is one strongly connected component, this is another. Okay? All right? So that is the partition of the graph into strongly connected components, right? Does it make sense? Yeah? A strongly connected component, this graph may be misleading. A strongly connected component need not be just a cycle. It could be more complicated than a cycle, right? Yeah? Any questions on the definition of strongly connected components? Seems okay? Yeah? Okay. Okay. So when you have a directed graph, you want to compute something more than just the basic reachability, but here are some interesting questions you can ask in a directed graph. So I have a directed graph and I have two vertices u and v, and I want to know, can u reach v, right? That's the most basic question, right? Now the second question you can ask is, given a directed graph and a vertex u, I want to find all the vertices u can reach, right? That's maybe a little bit more general question, yeah. And then I can ask, okay, what about the other way? I have a directed graph, a vertex u, and I want to know all the vertices that can reach u. This is different from u reaching them, right? I want to know all the vertices that can reach u. Yeah? That makes sense? Okay? Okay. Now you can ask, find the strongly connected component containing the node u. Okay? So remember, there are strongly connected components, right? I want to know what is the strongly connected component containing u, right? For example, if I give you this graph and I say a vertex B, you have to tell me B, E, F are the three vertices in the strongly connected component. Yeah? Okay. And now I can ask, is G strongly connected? That means, is the entire graph strongly connected, right? Is there only one component in this graph, or are there more than one component? And then I can ask, if that is not the case, compute all the strong connected components of the graph. So if I give you this graph, you have to give me this partition. Yes? Yeah? Yeah, because, there is nobody else. I mean, so H can reach G. See, look at G, right? Can there be any vertex in the same component as G? No, so that it's its own component, right? Yeah, a strongly connected component doesn't have to be more than one vertex. It can be just one. Okay. So this goes back to the definition of equivalence relation, right? When you have an equivalence relation, you get a partition into maximal components, right? So why is A not in a strongly connected component by itself? Because there is a bigger strong connected component that contains A. Yeah, that's important. They're maximal strongly connected components, right? Okay, good question. Yeah, all right. Okay, are these questions reasonable? Yeah. Okay, now let's start with the most basic question, which is, given vertex u, can I find whether it reaches V, right? Okay, that we can do, we have already seen it, right? You do a BFS or DFS or something, right? You'll get it. So, but what does it mean? That it's really a basic search we can do even in a directed graph, right? So what is a basic search in a directed graph? You want to start with a vertex u, and you want to find all the vertices that you can reach. And if V is in that, we're happy, right? Okay, so basic search is easily generalizes from undirected graphs to directed graphs, even though it has slightly different properties. It's a very simple algorithm, right? You start with vertex u, you maintain a set of vertices that you have already reached, right? And you keep expanding that set just like we did with undirected graphs, okay? Okay? So initially u is reached, obviously u can reach itself, right? The set S contains just u, right? And then how can we reach one more vertex? If from the current set I have an edge going out from that set, remember here the edges are directed, right? So if there's an edge going out, then I can reach one more vertex, right? Because I have all the vertices in S are already reachable. If I find an edge going out of the set S, I should expand my set S by including that vertex. And then I keep doing that, right? Okay? So how do we do that? We maintain, this is explore GU, which is very similar to undirected graphs. You initialize a set which is U itself, and then you keep increasing the set, okay? Okay, so this is, instead of doing it via the long code, you just, again, I don't want it to be DFS or BFS. I just want it to be, so suppose I start with B. What does B do? Initially the set S contains just B, right? Okay, so we look at B and find all the edges leaving B, right? Okay, what do we find? We only find E, so we add an edge and say, aha, okay, we found E. Our set now becomes E because we pulled out, okay? And then, we look at the set, any vertex. I don't care which vertex I pick from the set. I only have E, so I pull out E, okay? And explore E, right? I look at all the edges leaving E. Do I find anything new? Or do I find F and G, right? So I say, F and G. and I add them to, I pulled out this, so S becomes F and G. Sorry, H2. Okay. 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 And this becomes sorry, F, G, and H. And then I pull out anything I want. I can pull out F for simplicity, right? Yeah. Because this is a basic search, I'm not interested in making any. I just pull one thing out of the bag, right? Okay. If I pull out F, do I discover anything? I mean, I have an H to B, but that's already found, right? So there is no point, right? Okay. So my set becomes just GH now because F is explored. Then I pull out G. Do I find anything new? No. So my set becomes H, and then I say I pull out H and try to find something new. Do I find anything new? No. So I'm done, right? So that means you can prove inductively that at each step, S is a set of reachable vertices, and you maintain that property, and okay. And you can also have to prove think a little bit about why, if I have a path to a vertex, I'll eventually discover it. Okay, that's maybe a little bit harder to see, right? I mean, you have to think, am I going to discover? It is not hard to see that whatever I discover is reachable from the vertex I started out with, right? But you also have to think a little bit about why is it the case that every vertex that is reachable is actually discovered by the algorithm. Okay, what do you think is the reason? How can you convince yourself that's correct? Can there be a vertex that this algorithm won't reach if that is actually reachable from B? But how do you convince yourself that how do you prove it? I mean, it seems intuitive, no? So I mean, how do you convert the intuition into a proof? Yeah. Yes, but that's correct. Yeah. So, but why does this algorithm find that's true, right? So, but I'm not. I mean, why is it the case that I find everything that is right? You have to argue something about the algorithm, right? Yes. What is it that you want to prove by induction? Yeah, it's a little tricky, right? So one way you can prove it is an interesting property. So at the end of the algorithm, you want to prove that for the set you have, that the set you already explored, there is no edges leaving that set. Okay. You can prove it by induction at the end of the algorithm that there is no vertices, no edges leaving the set at the end of the algorithm. That's an important property of the directed graph thing. So what did you find at the end of this algorithm? What did this algorithm find? This algorithm found what set? This set, right? Okay. What is a nice property that this set has? There cannot be an edge leaving this set. There can be edges coming into this set. There are edges coming into this set, right? But there are no edge leaving the set, right? Okay, if you can prove that property, then you'll be okay, right? Because for everything that is in the set, you have a witness because you found this tree. For everything not out inside, there is no way to get out of this set. Okay, that's one way you can prove it. Okay, all right? So that's an important property. So every edge at the end of the algorithm has to come into the set if it is actually incident on any vertex. It cannot go out, right? You can maintain that property. Okay. Okay. So that's so it's a simple algorithm, right? It's a basic search. We call it basic search because we don't want to think about whether it's DFS or BFS. Yeah. Okay. So in linear time, you can find all the vertices that you can reach, right? Okay. So one important point that I would like to mention, which will come up in a different algorithm, how much time does this algorithm actually spend? Okay. In the sense that once I initialize the data structures, I start the algorithm, how much time does it spend? So the initialization has to take time, right? It has to take all the graph, initialize it. But once I initialize the data structure, how much time does it spend? I mean, this is an important point, will come up in another algorithm. That's why I'm kind of making a point, right? Good. That's a more subtle answer, right? You can say, yeah, it spends no more time than the entire graphs, right? But I claim it does actually a little better, right? If I initialize the data structure and I'm not counting that time, the amount of work this algorithm does is only the amount that B can actually reach. Okay? Yeah? That's a good observation that will come you handy when we do something more subtle. Okay? Right? Suppose I explode from G, I don't do any work, right? Because G has no outgoing edges. Yeah? Does that make sense? I mean, of course, I'm not counting here the initialization of the graph and stuff. That takes linear time. Okay, so that's a good point. Okay. All right, good. And then you also get this exploration tree, right? This is a comment I made, that once you find this reachability set, all the edges are coming into that. You can't have anything going out, otherwise you. Okay, now let's answer. So we have a tool now, right? What is a tool? Given a directed graph and a vertex, I can compute something, the most basic thing, which is what are all the vertices I can reach, right? Now let's go and answer all of these things using just that basic tool. Yeah? Yeah. No, I didn't say anything about connected graph. I just have a directed graph and a vertex U, and I can find all the vertices that you can reach. Yes. Let's go through this slowly. Yeah. So here is a question, right? We already answered 1 and 2, right? By this basic search. Yeah? Yeah. What about 3? What is 3? I'm interested in all the vertices that can reach U. Okay. What does it mean? In this graph, what is that set? What can reach B? Yeah, but A can reach B too. So what can reach B in this graph? Yeah. B, E, F and A, C, D, no? Yeah. This is a different question, no? I'm not interested in what B can reach. I'm interested in what can reach B. That's not the same set, no? Because it's a directed graph. Yeah? Is it clear what we're asking for? How will you find that? Using the same algorithm. Yeah? Well, that's even harder problem. So, okay, what is the most naive algorithm? Okay, you can, yeah, sure. Yeah, that's a good idea. That's another way, yeah. Yeah, okay, those are good ideas. So what he was saying was something even more naive, right? Which is he saying, for every vertex compute what it can reach, right? Okay. So you run n times the algorithm and then look at all of them and say, did this guy reach my vertex? And if it is, we put a tick on that, right? Okay. That takes n times of computation, right? N times n plus m, right? What you said. Okay, what these two are saying are a little bit more nicer, right? What you're saying, it looks like, I'll rephrase it. We just reverse the graph. What does it mean, reverse the graph? We take all the edges and flip them. Okay? Okay. Is it clear what I get a new graph, no? Yeah? So given a directed graph, the reverse of the directed graph is a graph where I reverse the orientation of all the edges. Okay. So in that graph, if I do the reachability computation, what will I get? you will get what I want, right? Yeah, because what does it mean that a vertex can reach my u in that G? A vertex can reach u if and only if u can reach that vertex in the reverse of the graph. Okay. Now you say, how long does it take for me to convert the graph and make it into a reverse graph? I mean, the reverse of a graph. Can you do it in linear time? Yeah. So given a graph, directed graph, I can create a copy of it where all the edges are reversed in linear time, right? Yeah. You make all the incoming edges outgoing edges, right, and vice versa. Yeah. Okay. So that is conceptually the easy way of thinking about it, right? Yeah. Is it okay? Everybody okay with that? Okay. Now maybe you don't want to create a copy of the graph, right? That's actually not very nice, right? To create a copy of the graph, but you can simulate it in place, right? In the sense that we look at the algorithm, what is it doing? It is looking at outgoing edges, right? So instead, but in the reverse of the graph, what would you do? You would basically flip all the incoming edges and make them outgoing edges. You can simulate that without actually making a copy of the graph and then running this algorithm, right? What can you do? Instead of exploring from u, the vertex u, the outgoing edges, you explore the incoming edges, right? Okay. If you don't want to make a copy, you can do that too, right? Is that okay? Yeah. If you had incoming and outgoing edges, you can just simulate this algorithm without actually creating a copy. But conceptually, you should think, I'm reversing the graph and I'm doing the same computation. Yeah? Yeah, this is the representation, no? Remember, you have to think of the representation a little bit. The representation you should think about is something like this, right? I only have outgoing edges, but I also have a list of edges. So I can scan all these edges and find, and I have pointers from this to that, right? All the edges are, all the edges are numbered. You don't have to think of as pointers. This is static data structure, right? So every edge has a number, every vertex has a number. So just, and each edge remembers what are the two endpoints. So using that, you can create the reverse very easily. Yeah? Okay? Okay. So all right. So that is easy. Okay, now let's do something, the next step. So you can do this, right? How long does it take? Linear time, right? What about 4? So what is 4? I want to find the strong connected component containing the vertex u, right? So for example, if I give you B, you have to give me E and F, B, E, F, right? If I give you G, you have to just give me G. If I give you C, you have to give me A, C, D, right? So how will you solve that? So I give you a graph and a vertex, and you have to give me the strong connected component containing that vertex. So in this graph, if I give you this G and I say B, what is the strong connected component containing B? That's correct, right? He's saying, what are the vertices in this strong connected component? These are the vertices that you can reach and they can reach you, right? Yeah? So it's an intersection of those two sets, no? I compute all the vertices I can reach and I compute all the vertices can reach you, and their intersection is what I'm looking for, no? Yeah? No, intersection is not constant time, right? Okay, but I claim in general intersection is a hard operation, right? But how will you do the intersection here? No, but again, remember that our vertices are indexed, no? Just 1 to n, right? So when I find, for example, I look at B and I find all the vertices that B can reach. What is all the vertices that B can reach? B, E, F, G, and H, right? Okay. How do I store that information? Yeah, so you have to be a little careful, right? So maybe, okay, these are all numbers, right? So I have to number them here, it is not numbered, but let's number them, right? Just, arbitrarily, I'm making up some numbers, right? Okay. I claim something simpler can be done, right? So now, when I do the reachability from B, what do I get? You can think of it as a list, right? you can say, the things I can reach are 1, 2, 6, 7, 8, right? And what can reach B? Okay, now if I want to think of intersection, it is a bit of a hard thing, no? If I just give you two sets and just find intersection, it's a little bit hard, right? Okay, if you think of a set intersection that way, you may think, oh, I have to look in, but you have a little bit more careful. You can be more careful because, yeah. Yeah, so I mean the thing is, these are not arbitrary sets, right? These are just vertices, right, of a particular graph. So you can store this set as a Boolean vector of size n, right? Yeah, you say 1 if it is in this set, 0 if it is not in the set, right? You just store it, right? Because it's like a radix sorting or whatever, right? Because these are just vertex indices. You can just store n array with zeros and ones to represent this set, and also another array for this set. And if both are 1, you output it. If it is not, okay, the amount of time you take is n, right, where n is the number of vertices, okay. When you think of them as sets, you are worried about, arbitrary sets, but here they're not arbitrary sets, right? They're just sets of vertices in a graph, and you've already spent linear time, so it's okay, right? Even though the sets are small, you can spend n time to do the intersection. Is that okay? So it's, in addition to the linear time, you have to spend a more linear time, so you can do the intersection. Is that okay? Yeah, okay. So this is easy. How about if G is strongly connected? How do you know if there's only one component? It's not a difficult question, right? If given a vertex U, yeah. Now I claim it's the same as the previous 4, right? Because you pick an arbitrary vertex and computes its strongly connected component, and if the entire vertex set, you're done. Otherwise, no, right? Yeah, is that okay? Okay. All right. Yeah. Okay. So this is also in linear time. Okay, but what about the last question? How do I compute? So basically, I give you a graph, and you say you have to give me this list, this partition. That's a harder question, right? Why is it a harder question? From just reachability, we cannot solve this without. So what can you do? Can you first how efficiently can you compute it, right? So knowing what we know, can we do something for this problem? Yeah. Yeah, you can do that, right? So you don't have to take it out, it will help you take it out, but you start with a B, you found this strongly connected component. And if the entire vertex set, you're done. Otherwise, you find a vertex which has not been in that set, find its strongly connected component, right? So you'll find, if you start with B, you'll get BEF, you put it aside, or you know that that's done. Then you pick another vertex which is not BEF, and say, okay, maybe I start with H, and you'll find just H, you're done with that. Then you maybe pick C, and you'll find A, C, D, and then what is left, and then G, and so on, right? How many times do we need to do this? Potentially n times, right? So the number of computations we do is n times n plus m, which will be n square plus nm. Yeah? Okay, it's okay, at least we can solve it, right? Yeah? Agreed? Okay. Now the question is, can we do it more efficiently? Okay. Do we need to do this algorithm, or can we actually find all of them in linear time? The whole structure in linear time. It turns out you can, but it requires a non-trivial algorithm understanding of the graph structure. Okay? So it's not obvious how to do it, but you can do it. Okay? So that's one thing. We'll just describe the algorithm, but okay. So we solved those questions. So okay, we already discussed this. So now let me tell you why graph search is so powerful, right? Here is a simple example of a problem in Jeff's notes or something like that, right? You'll see some of these kinds of problems, right? And look at the problem for a couple of minutes, right? We play many of these kind of games, no, as kids and stuff, right? It looks a bit complicated, yeah. Is the puzzle clear? Yeah. Yeah. Okay, so what happens? You are given a large n by n square, right? Yeah. And the two tokens, the red token and the blue token, the red token is here, the blue token is here, right? What is the goal? You want to swap this. That means that you want to get this guy there and that guy here, right? Yeah. What are you allowed to do in a one move? In one move, you can choose. Do you want to move the red token or the blue token? Yeah? Okay, so, but if you choose the red token to move, what is the constraint? That you look at the number on the blue token, what is it? 2, right? That means you are allowed to move either this way, up to 2 moves, right? Okay? So, I mean, you can even decide to choose one move if you want. Yeah? Okay? And so here you move it 2 steps, and so now it is here, and now you can move the blue token 3 moves because this number is 3, right? And then because that is 3 now, you can move this way to 3 and so on, right? Okay? You managed to swap these 2 tokens, right? Okay. Now maybe if I give you some zeros in this squares, clearly you can't swap them, right? You can't even move. Yeah? Okay, now I give you this puzzle and I want to know is it solvable or not, right? Okay? Okay, you can start doing it on a given puzzle, right? But how do you solve it algorithmically? Okay? So this is n by n now, right? You know, if it is a small fixed puzzle, then you can enumerate everything you want, right? But now I have n by n puzzle, right? How do you solve it algorithmically? Can you reduce it to a graph problem? Graph reachability problem. How? What are the vertices? What are the edges? What are we trying to do? Yeah. No, but precision. What is each of it mean? What are the vertices? The entire state of the puzzle? Okay, the entire puzzle is one vertex. The state of the puzzle is one vertex. Okay. Okay, so the state of the puzzle is where are the locations of the 2 tokens, right? How many vertices will you get if you do that? No, okay. There are n by n puzzle. What is the number of states we have? It's n by n puzzle, right? But we have 2 tokens, not 1. Yeah? N to the 4, no? No, remember the side of the square is n, right? So to specify the position of one token, I need n square, no? 2 coordinates to specify that, right? But I have 2 tokens, right? So I have to specify this and specify that, right? Yeah, it's like a product construction, no? Okay, yeah. So that is our state of the system, no? Okay, what are the moves allowed? If I have 2 tokens, I need to know, can I go from this state to another state? Can you figure that out? Yeah? How do you know whether if the 2 tokens are here and I look at another set of 2 tokens, can I go? Can you decide that quickly? That's the rules of the game, right? The rules of the game tell you whether if I am in this state, I can go to this state, no? So you draw edges between two vertices if that is allowed as part of the move of the puzzle. Yeah? Agreed? So now what are you trying to solve? What problem are we trying to solve to see if the puzzle is solvable? Yeah, you're going to go from the initial state of where the tokens are to the final state where they're swapped, no? Yeah, or maybe I can even solve it where some other location. Yeah. No, just reachability, no? So I have a directed graph where my vertices are all possible locations for the tokens, right? And my initial, and then the edges of the graph are, if I can go from the given current state of the tokens to the next, to that other state by one legal move, we put an edge from this vertex to that vertex. It's a directed graph. And then we are simply asking the question, can I go from the initial state, which is the two tokens are here, we know those positions, to the final state where they have to be here? It's just reachability. Is there a path from the initial state to the final state? No, this is a state, that is a state. They are different states, right? Remember, the state specifies the red token differently from the blue token. So it's an ordered pair. That's why we have n square, n to the 4 vertices, because I have to distinguish the red token from the blue token. Okay? Agreed? Okay. If you just try to solve it another way, it will be very complicated, no? But you can easily reduce it to a graph search problem, right? Yeah? So a lot of simple things like this can be reduced to graph search. Okay? Agreed? You don't really need to know anything about the rules of the game, really, right? I mean, the rules of the game are completely encoded by the edges of the graph. Yeah? I can create some bizarre rules. As long as I can create that graph, I can solve this by graph search. Yeah? Question? No, I mean the blue token, the red token went to this position and the blue token went to that position. That's what, I mean, this is what, that's a puzzle, but you can, that's the goal of the game. Can you go from this configuration to that configuration? Yeah? Questions? Yeah? Okay, that's the power of graph search. Okay? Okay, now again, I want to emphasize this directed versus undirected because it will come up. So here is another problem, like to test something, right? So I give you an undirected graph, right? I emphasized it, and two subsets of nodes, a red guys and a blue guys, right? They are distinct and they are non-empty. No, it's a different problem. Okay, I want to know whether every red node can reach every blue node. Okay. Okay, I have a big graph, right? There are some red nodes and some blue nodes. Okay. Make sense? Yeah? And I want to know, can every red node reach every blue node? How will you solve it? First, don't worry about the running time. How will you solve it? First, you have to figure not the efficient algorithm, but some simple algorithm. Does the question make sense? Can every red node reach every blue node? Yeah. I mean, you're almost there. You just check the component containing a single red node and check if all the red and blue nodes are in that. Right? There could be other nodes which are not in that component. Okay, so very good solution which most people don't get. Okay, see, observe that the graph is undirected. Okay, if the graph is undirected, then every red node can reach every blue node if and only all the red and blue nodes are in the same connected component. Yeah, connectivity in undirected graphs you should think of as connected components, right? Okay, so you can do it efficiently by simply finding the connected components, yeah, that you can do, and then checking whether all the red and blue nodes are in the same connected component. Okay, okay. Why am I saying this? Because if the problem is a directed graph, then the solution doesn't work, right? What is the solution you will do in that directed graph case? If I want to answer this, how will I answer it in a directed graph? What is the naive solution? Which he came up with a clever solution, which I was hoping he wouldn't, but what is the naive solution if you want to answer this question? Don't do anything clever, right? Right. So check every red node and see if it will reach all the blue nodes, right? Okay, that requires the number of red nodes times search, right? That will work, right? Okay, but the running time of this algorithm in a directed graph will depend on how many red nodes are there, right? Times the linear time for each of them, right? While in undirected graphs, we could just do one linear time and finish it, right? Because we just had a structurally different observation about undirected graphs. Okay, and you cannot solve this problem in linear time and directed graphs. There's no way. Okay, so that's the difference between directed graphs and undirected graphs. The reachability is different. Yeah, the symmetry helps you. Okay. Okay. So here is another variation of this, just to make you think again, right? So the small twist of the problem. I now have a directed graph, again red and blue nodes. I want to know whether every red node can be reached by some blue node. Okay, okay. So the quantification is important. Okay. Okay. So what do you understand from this question? Okay. Yeah. Yeah, that's a solution, right? The question is the question clear? Ish. Yeah, I'm trying to understand I'm trying to make sure that people understand what the statement is asking, right? There's a path from the, right? Yeah? Is that clear?
So that don't mean one blue node has to touch all of them.
Right. Yeah, that's not what it means, right? It says that, for every red node, there must be some blue node. There exists a blue node that can reach that red node, right? Yeah. So how will we solve this problem efficiently? Well, you could try, right? For every blue node, you do the computation of what it can reach, right? And then tick off all the red nodes it reaches, right? If all the then you do it for the next blue node and the next node and so on. And if you do it for all the blue nodes and all the red nodes are ticked off, then you're happy, right? But can you do it better than just doing it like that, right? Okay. Remember, it's a directed graph, right? Okay. And his solution is better because here is a trick that is a important and a powerful trick, right? So here are, okay, let me use blue, right? Here are the blue nodes, right? Now this is one blue node, this is one blue node, this is blue node, and what I can do is I can create a new super blue node, okay? Add it to the graph, to only the blue nodes, right? And then do a reachability from this single node, right? And check if this node can reach all the red nodes, yeah? That's the same as what we're asking, right? Okay? So, okay, what do? I create a new vertex. This is a very standard trick in graphs, right? You add a new vertex, super vertex, connect it to a subset of the, what vertices am I connecting it to? A subset of the, all the blue nodes, right? Okay, and then I just compute the reachability from this node in this new graph, right? And if I find all the red nodes, I say yes, otherwise I say no. But that's the same thing, no? What I'm asking. Except that now you see that you can do it in linear time rather than doing it one for every blue node, right? It's another way of thinking about it, which is a bit more complicated, is to say, like he said, start exploring from all the blue nodes simultaneously, right? You start with all the blue nodes and kind of grow your search. That's a little conceptually, that works, but this is a more easier way to do the reduction, right? Okay, it's clean. you can use a previous algorithm as a black box, yeah, reachability. Does that make sense? Okay, that's very important in graphs. Graphs are extremely powerful because of this ability to do reductions with them, okay. You can model a lot of problems, you can do reductions using them, and so they're extremely powerful, okay. And we'll see that they also, you can, yeah, okay. So that's something that you should keep in mind about graphs, that the ability to do these reductions is the skill that we would like to obtain from this part of the course, okay. Okay. So I want to go back to that problem of computing all these strong connected components of this graph, right? Remember I said that there exists a complicated algorithm which can actually do this in linear time, okay? So it's not simple, even though the algorithm is basically 10 lines of code, okay? Or 20 lines of code, right? It is very simple, but understanding its correctness and conceptually why it's true is a long time, right? So I'm not actually going to prove all of that, but I'll get you there by doing something else, right? I mean, since that you'll see all the ingredients, and but we won't remember the algorithm. Okay, so you need to do graph theory to derive algorithms, okay? So it's also important to understand the structure of graphs, right? So here is an important concept that we'll use. Okay, so recall that, what are the strong connected components in this graph? These three, this vertex and this vertex, okay? Okay, so to understand a directed graph, we should take these strong connected components and shrink them, okay? Okay, what does that mean? That we're going to create a new graph, okay? What does the new graph have? It have one vertex for each of the strong connected components, okay? And then we put an edge from this vertex to the other vertex if there is an edge from some vertex here to some vertex here, okay? Okay? So here is a new graph I'm creating from the old graph, okay? How am I creating? I look at the strong connected components and create one vertex for each strong connected component, okay? So we had 4 components here, so I had 4 vertices here, okay? And now I have to tell you what the edges are. When do I add an edge from this vertex to this vertex? Because there was some edge, right, from some vertex here to some vertex here, right? Is there an edge from at least one of these vertices to one of the vertices here? There is, right, because E has an edge to edge. So I add one edge from this, right? So is this graph clear how we created it? Yeah? Okay, so this is called the meta graph of this directed graph, or the strong connected component meta graph, or GSCC. There are many names for it. Okay, is it clear? Yeah. Okay. No, it's a bit more than that. No, this is more complicated graph. No, it's not. It has. Yeah, I shrink them. Think of taking this thing and shrinking them, right? Right, into one vertex, right? I mean, this graph is obtained by taking this thing, taking the strong connected components and shrinking them into one vertex each, right? Except that I'll get multiple edges, in which case I just keep only one edge. Does that make clear? Yeah, that's another way of thinking about it. Is graph clear? Yeah? Okay, what property does this graph have? This graph, it has some nice property, yeah? It cannot have a cycle. Can it have a cycle? This graph cannot have a cycle. Why can't it have a cycle? Cannot it have a cycle? Yeah? Yeah, right? If it has a cycle, all those should be in the same strongly connected component, right? And we would have shrunk them together, no? So this does not have a cycle, right? Okay. Okay, so then what happens is that if you have a directed graph and look at this graph, it creates what's called a directed acyclic graph. Okay? All right? So if you have a directed acyclic graph, what is its what does its graph look like? This graph. If I give you a directed acyclic graph, what are the strong connected components? of a directed acyclic graph? Each vertex is in its own strong connected component, right? Because you can't simplify it any further. And so if I take this graph of this meta graph of that, what do I get? I get the same graph, right? If I take a DAG, it's called DAG, right? I can't simplify it any further, right? At least in this way. So this is one way to understand it. If I have a directed graph, I can always take its strong connected components and create a directed acyclic graph. Now, so that's useful, right? Now we have to understand what properties do directed acyclic graphs have, right? They have many nice properties, okay? And they are very important class of directed graphs, okay? And they'll come up in a lot of applications, including dynamic programming and stuff, right? Okay? So we already saw that if I give you any directed graph, the meta graph has no directed cycle, so it's a directed acyclic graph. So now we have to understand what properties do directed acyclic graphs have, right? Can we understand something about a directed acyclic graph? So this is a directed acyclic graph, okay? So sources and sinks, right? You know, what is a source vertex in a directed graph? A vertex which has no incoming edges, only outgoing edges, okay? Agreed? What's a sink? A sink is a vertex which has only incoming edges. Does it make sense? Terminology? Okay. So in this graph, this is a source and this is a sink. So this is not a source or a sink because it has incoming and outgoing edges. Okay. Every DAG has at least one source and at least one sink. They don't have to be different because if I have one vertex and no edges, this is both a source and a sink, right? Okay. Every DAG has at least one source and one sink. Why is it true? Sorry? Okay, what is a source and a sink? Sorry? Squares? Okay, I can go back to the squares. No, this is, remember, now I'm not worried about the meta graph. I'm just saying I tell you that a graph is a DAG. What does it mean it's a DAG? There is no cycle in the graph. Right? Yeah. Why is that? That's true, but why is it true? Yes, so we're trying to formalize that, right? You want to claim that if the graph has no source and no sink, then it must have a cycle. Or conversely, if there are no cycles, then it must have a source and a sink, right? Yeah. How do you make that intuition? So suppose you give a cycle, clearly it has no source and a sink, right? Yeah? Right? Makes sense, right? If a cycle. So, but I'm claiming there are no cycles, there must exist a source and a sink. I mean, you can have a source and a sink and a cycle, right? So you have to be careful, right? I'm saying if you don't have any cycles, there must exist a source and a sink. So he had the right intuition, right? Okay. So here is one thing you can do, right? Suppose you start at an arbitrary vertex. If it is a source, you're happy, right? You're done. If it is not a source, what does it mean? It means that, I mean, okay, suppose it's a sink, we are done. Okay, we can do it the other way, right? If it's a sink, we are done. If it's not a sink, what does that mean? It has some edges going out, right? Yeah? So let's take that edge. It has some edge, so let's go to the next vertex. If it is a sink, we are done again, right? If it is not a sink, what does it mean? It has one more edge going out, right? So we can go to the next vertex, okay? So what happens if I keep walking like this in the graph? Either I'll find a sink, in which case I'm done. If I don't find a sink, what will happen eventually? I can't keep going because the graph is finite, right? So I'll end up visiting a vertex that I've already started with. But then that's a cycle, right? The first time I do that, I'll stop because that's a cycle. So, but I can't do that. So that means I have to end up with a sink. Yeah? Agreed? Okay. Now, by the same argument, I can walk backwards and get you a source, right? Yeah. See, if I'm a source, I'm happy. Otherwise, I'll go back, right? But okay, does that make sense? Okay, to be more formal, you can do the following, right? this looks like a so-on argument, right? What is this? You can formalize it by saying, take the longest simple path in the graph, okay? And you can prove that the end of the start point of that path has to be a source, and the end point has to be a sink, right? Why? If I take a very longest path in the graph, simple path, if the last vertex is not a sink, what does that mean? I have one edge going out, right, of that. I can take that edge. If I find, I can't create a cycle, but then that will be a longer path, which will contradict the fact that I chose the longest path. So that must be a sink, okay? And so this is a little bit trickier way of thinking about it, right? It's not as intuitive, but it's a more formal way of arguing it, okay? All right. So every DAG has a source and a sink, right? It can have multiple, right? So you can see this, right? Okay. So the most important thing, whenever you think of a DAG, you should think about a topological sort of a DAG. Okay? So what is a topological sort of a DAG? Is an ordering of the vertices from 1 to n such that the edges go only from the left to the right, or from the lower numbered vertices to the higher numbered vertices. Okay. So what does a DAG really mean, right? In terms of what does a DAG tell you? DAG is what's called a partial order, right? Okay. Okay, what is a partial order, right? A partial order on a set of elements is a relation, right? In saying, this is smaller than that, right? Okay. It only tells us for some things, right? Take a set of numbers, right? If you take a bunch of integers, we can order them completely, right? Yeah? We can order them completely because of the ordering relation on numbers. But there will be objects where I can only say this is smaller than that, right? I can't compare every element, right? That's called a partial order. Partial order because I can only compare some elements, but there are no cycles in that. If there are cycles in that, that doesn't make sense, right? They are not a partial order. So a DAG is like a partial order, right? I'm giving you some relationships of less than, right? So what is the topological ordering of a DAG? It's like saying, I can always convert a partial order into a complete order in a consistent fashion, okay? So that's just for mathematical thing. So if I give you a DAG, I can always order the vertices number the vertices from 1 to n, such that the only edges are going from a lower numbered vertices to higher numbered vertex. Okay, that's called a topological sort of a DAG. Okay, whenever you think of a DAG, think of a topological sort, right? Just for strategic reasons, if not for anything else, right? Okay. So how do we prove that every DAG has a topological order? First, so one thing we can claim is that a directed graph can be topologically ordered if and only if it is a DAG. Okay. So not only can we do it only if it's a DAG, but we can only do it if it's a DAG, right? If I have a cycle, can I do a topological order? Can I order the vertices of a cycle so that only edges go from left to right? I cannot, right? If you put any order, I have to come back, right? Because the cycle will force me to come back, right? Yeah. So if I have a cycle in the graph, I cannot create an ordering on the graph, right? But if there's no cycle, I can create it. How do you prove that? That if I have a DAG, I can always create an ordering of the graph. Hint. We already saw that every DAG has a source. No, it has multiple thing, right? Okay. Okay, here is an algorithm to create a topological ordering for a DAG. Every DAG has a source, right? Yeah, we saw that. What does the source mean? No incoming edges, right? Yeah? So it is safe to put it in the first position, right? There is no way any edge will come into it. Okay? You pull out the source, put it in the first position, and then recurse on the remaining DAG. Okay? Okay. So here is an algorithm. What are the sources in this DAG? How many sources are there? No, C is also a source, right? It's a source and a sink, right? So, okay, I can start with any source. Which source do you want to pick? A, okay. Now I remove A. What are the sources in the remaining DAG? If I remove it, B, C, D are the sources, right? Pick anything you want. Maybe I'll pick D, right? Okay? Now I remove D2. What are the sources in this DAG? B, C, and F, right? So maybe I'll pick now B, right? Okay, now I remove B. What are the sources in this DAG now? E is now a source, and then I can put C, right? E, then C, and then I can put G, and then F, and so on, right? Okay, and then H, right? There is not unique topological sort. There could be many things. Okay. Now, why is this correct? Because if you pull out a source, if by induction you can prove that the remaining order I create recursively is a topological sort, right? And I put this guy in the front, there is no way an edge is coming in because he's a source, right? You can prove it by induction, right? Okay? And there's not one topological sort, there are many topological sorts, right? Yeah? Agreed? Okay? Okay. So now, so there are many topological sorts. What is the DAG with the smallest number of topological sorts? How does it look like? Just to make sure you understand. Which DAG has the smallest number of topological sorts? And what does it look like? Every DAG has at least one, right? Is there a DAG where there's only one topological sort? Yeah? Single one? No, I want a large graph, not one, right? Any n, not just one, yeah? Yeah, it looks like a path, right? 1 connects to 2, connects to 3, connects to 4, connects to 5, and I can have more edges, but I have one long chain that cannot have any other topological sort, no, other than just 1, 2, 3 up to n, right? That's only unique topological sort if I have a path which is going from left to right. I can add more edges, but if I have a total order already, then that's it. There's only one total. What is the DAG which has the most number of topological sorts? If I have n vertices, how many different topological sorts can I have? Yeah? Sorry? Completely connected. No, but it has to be direct. It's an acyclic graph, no? Okay. I claim if there are no edges, then every ordering is a topological ordering, right? I mean, there are no edges, right? Nobody is related to anybody, completely empty, right? Then there are n factorial different. Everything is a valid ordering because there are no edges, right? So that's the extreme case, right? Okay. One extreme case is no connection at all, so I can do whatever I want, right? The other case is I only have one path, then you're stuck. That's the only topology. Yeah. Okay. Okay. Now, okay. So here is the question, right? How fast can you implement this algorithm? Can you do something? I mean, I want to find this, right? How fast can you implement this algorithm? So, I mean, we have an algorithm, right? If I ask you to implement it, what would you do? Right? I give a graph, right? How will you create a topological sort? Okay, implicit in this question is, can you check whether a graph is a directed acyclic graph or not, right? Yeah? I say, I give a graph. I don't tell you whether it's a DAG or not. Yeah? And I say, is it a DAG? If it is a DAG, can you create a topological sort? He's saying BFS or DFS to detect a cycle. We haven't even figured that BFS or DFS, no? How do we know? Yeah, first, how will you check whether a graph is a directed acyclic graph or not? Sorry? No, it's not so simple, no? Yeah? Not as simple as that. No, yeah, I know, but you have to be more precise than that, right? The search may visit vertices, right? A question, yeah? That's a very good answer, right? If I have a graph and I don't have a source or a sink, what do we know? It must have a cycle, no? Yeah? So can we check whether a graph has a source? I mean, right? Okay. But does the fact that a graph has a source or a sink doesn't mean the source doesn't mean it doesn't have a cycle, no? I can have, right? But you can run this algorithm, right? What we can do is if I find a source, I can take it out, right? It is not going to participate in any cycles anyway, right? And then continue the algorithm, right? And at any point, if you get stuck without a source, then we know there must be a cycle, right? Yeah? Yeah, is that clear? If I try to find a source, if I don't find a source, I know I have to have a cycle, right? Okay, it's not easy to find that cycle maybe, but I do know there is a cycle, right? How do you find it? If there is no source, how do you find out whether there is a cycle? I gave you the proof earlier, right? Can you convert it in an algorithm? Yeah. So the reach thing doesn't give you a cycle, no? Yeah, a little bit more careful. Yeah, yeah. I know, but but that is true. But how are you guaranteed that the traversal will hit a cycle? Your work, I mean, right? It's not obvious, no? Yeah. But see, how did you argue that a DAG has a cycle as a source? We said start at any vertex, keep walking, no? Okay. Okay, if there is no source and no sink, if you keep walking, you will hit a cycle. The proof will give you, right? You just do a walk. Okay? If there's no source and no sink, you will find a cycle by just doing basically a random walk. Yeah? Alright? Okay, anyway, you can do many things. But okay, here is the algorithm to check whether a graph is a cycle or not. You check whether there's a source, take it out, and then keep doing it. Either you get stuck, in which case you know there is a cycle, or you keep doing it and you'll get a topological sort, right? Yeah? How fast can you implement it? How fast can you find a source? How will you find whether a graph has a source or not? You just have to check the in degree and out degree, no? You just have to count. If the in degree is 0, then it is a source, right? You don't have to do any walking and stuff, right? So it's very easy to find whether a graph has a source, no? By just keeping track of the count of the degrees, in and out degrees, right? But once I remove the source, what should I do? I can update the count, no? Yeah? I remove this vertex, I look at all the edges going out of it, and update the counts because I want to find the counts in the new graph, right? Okay? How long will it take? It takes how many edges I have, right? Okay? So I can remove it, I can update the counts, and I can find whether the new source or not, right? Okay? So I want you to understand that you can implement this algorithm in linear time if you're a little bit clever. Is that clear? This algorithm of repeatedly finding the sources and removing them can be implemented in linear time by just keeping track of the count and keeping track of a bag of sources. Yeah, is it okay? Yeah? Yes? Yeah? Exactly, right? How do you find a source? You initially compute all the in degrees and out degrees. Look at all the guys with in degree 0. Keep them in a list, a bag. I don't care which one there is, right? Okay? You can find all the vertices, you can compute all the in degrees and out degrees, and look at all the vertices with in degree 0. They're all sources, they will never change. So keep track of them in a bag. Okay? Bag meaning a list, right? Okay? And take anybody out, put it aside, update the counts of all the vertices now that I've removed this vertex, right? How do you do it? You scan all the edges out of this guy, reduce it. Whenever a guy's in degree goes to 0, it becomes a new source. No, it takes, the work you do per vertex depends on the number of edges it has. But once you see an edge out of the vertex, you'll never see it, right? Because I removed it from the graph. Okay, let's run it on this graph. Do you want to run it on this graph? Yeah. Yeah, D has become a source because the in degree of this has gone down after remove A, right? Yeah, is that okay? Yeah, questions? Yeah, no? Okay, think about it. If you have not seen that, you can implement it in linear time. So this is important because what I'm trying to say is that even though the algorithm at a high level is very simple, implementation also matters, no? How you do it, it is linear time, right? Okay. Okay, You can answer these questions in linear time, right? You know, given in a directed graph, how do we check whether it has a cycle and output 1 if it has 1? By this algorithm, right? It's one way to do the algorithm, right? You find a source. If you don't find a source, you know there is a cycle, right? If you don't find a source or a sink, you will find a cycle. How do you find whether an undirected graph has a cycle, by the way? If I give you an undirected graph and say, does it have a cycle, what will you do? No, undirected graph. There is no notion of strongly connected components in an undirected graph. It only makes sense in a directed graph. Okay, that's why I keep stressing undirected graphs. You have to think differently. Okay, you know, but first let's find. Can you check whether undirected graph has a cycle or not? Yeah. Sorry. Yeah, so you know, see again, you don't even have to look at the graph. If you know the number of edges and the number of vertices, you can tell whether undirected graph has a cycle or not. When does an undirected graph have a cycle? Right? No, I mean that's not quite true if you don't know it's connected, right? If I tell you it's connected, when does an undirected graph have a cycle? It has at least one more than the number of vertices. I mean, if it has a number of edges is at least n, then you know it's a cycle, no? Okay? But maybe the graph is not connected, then you can't use that, no? So compute any connected component. If it has any edge other than a spanning tree you created, it must have a cycle. Yeah? Agreed? Yeah? Or compute a connected component. Each of the connected components, right? And look at how many edges are there in the connected component, right? Okay. It's a very different solution than in a directed graph. Okay, it makes sense? You compute the connected components, check the number of edges in each connected component, then you know whether it's a cycle or not. Every edge which is not there in the tree that is generated by a search must create a cycle in an undirected graph, no? If you add that edge to the tree, it will create a cycle. Okay, so it's important to understand the directed graph and undirected graphs are very, you know, different in their structural properties, and okay, that's something that you should keep remembering at least when you do graphs. Okay, next lecture what we will do is we will study depth first search, not because it is just yet another search algorithm, but because it explores the graph in a very particular fashion, and that has very nice properties that you can exploit algorithmically. Okay, so we are going to do that properties of depth first search in the next lecture.